So the fine will be open book on the second 5 chapters, but you're responsible for the first 5 chapters too. It's just that the problems aren't going to be focused on the first 5 chapters. It's possible that some of the problems will require knowledge of linear independence, or that mission operators have mission matrices have complete sets of state. I don't know. I haven't made the thing up, but the focus will be on the second 5 chapters. So, other than that, what question? What does anybody have a question? What about, what would you like me to talk about? We finished covering those chapters, and you want to hear about group theory?
Bessel equations? Bessel equations?
So you want to hear about Bessel's equation? Where's the chalk? Well, I might as well open that part of the book on the screen. So, there's Bessel's equation. It's not, however, in self-adjoint form. The self-adjoint form is later. In the book, it's 1011 there. And so the function that I've called p of x is simply x. And you can, of course, set k equal to 1. But for arbitrary k, it looks like that. Is this something you want explained with regard to?
I just find Bessel's functions or Bessel function.
Huh?
I just find Bessel function equate or Bessel function problems confusing. That's all in general.
You want to see some solutions of Bessel function problems?
Sure.
That's what I did in the problem session yesterday.
I couldn't make it.
Which you skipped, yes. So let's see. Well, one problem that I did yesterday, but that's sufficiently interesting that maybe I'll do it again. You recall the generating function for Bessel functions is z over 2 u minus 1 over u is the sum u to the n jn of z, And if we set u equal to e to the I theta, then this is e to the z over 2 e to the I theta minus e to the minus I theta is sum e to the I n theta Jn of z. And this n is going from minus infinity to plus infinity. So this allows one to find an expression for Jn in terms of what's on the left-hand side, and what's on the left-hand side is really e to the, let me get the sign right, e to the I z sine theta. So in other words, we divide by I, multiply by I, we get e to the I z sine theta is then this sum here. And we can project out Jn by doing an integral 1 over 2 pi, integral, let us say, minus pi to pi, e to the minus I n theta, and then what's left is this on the other side, which is plus I z sine theta, d theta. So that gives you an integral formula for Jn. And now that I think about it, you can see from this what happens if you change n to minus n, and in particular you can see that j minus n of minus z would put a minus sign here, and let's see, this isn't actually as simple as I thought. All right, let me not go in. Right, okay. One needs a few more steps to get there, so let's take that expression and now change the interval of integration to zero to pi, and for the negative range we'll just have two exponentials, minus I n theta plus I z sine theta, and then for the negative range we're going to have theta negative, so we have e to the I n theta minus I z sine theta. And now this you can recognize as a cosine term. So this is 1 over pi, integral 0 to pi, cosine of z sine theta minus n theta d theta. So that's I would imagine it was a very surprising result to the people who first worked it out. Here the Bessel function was originally defined as an infinite series involving z to the n, and now we've re-expressed that as an integral of trigonometric functions. But the cosine is even, and so this is equal to 1 over pi cosine of minus z sine theta plus n theta d theta. But this is j minus n minus z. So you have that identity. Jn of z is j of minus n of minus z. So there are various other relations that we can have. We can also write Jn of z as 1 over 2 pi, an integral from 0 to 2 pi of e minus in theta plus iz sine theta d theta. So here we're just changing the interval, but since this function is periodic with period 2 pi, we can just shift it forward by pi, and it's the same integral. And or equivalently, we can write it as 1 over 2 pi, integral minus pi to pi, e to the minus I n theta plus pi, e to the I z sine theta plus pi d theta. So this is the same integral, but instead of shifting the interval of integration, we're shifting the variable of integration. And now the e to the minus I n pi is just minus 1 to the n, and so this is equal to minus 1 to the n over 2 pi, integral minus pi to pi, e to the minus I n theta plus I z sine theta d theta. Now that's the same as Jn of z, but, right, so what we've derived here is that this is minus 1 to the n j n of minus z. Well, no, I skipped a step, I think, so let me. So we'll get there in a moment, but let me first go back to this and oh wait, that was right. I forgot to do the sine of theta plus pi. The sine of theta plus pi is minus sine of theta. So this is a minus sign. So now if we look at that, we see that that is minus 1 to the n right, minus 1 to the n jn of minus z. So comparing those two, you can see that this is, that that's the case. Minus 1 to the n jn of minus z. So that's a second identity. And the jn of z is minus 1 to the n jn minus z. There are various ways of getting recursion relations. Let me instead maybe go to the back to Bessel's equation and just change variables. Or just start with the original form of Bessel's equation. So that's the second derivative of Jn plus 1 over z dJn dz plus 1 minus n squared over z squared Jn of z is 0. Now if we replace z, we set z equal to, let us say, ax, and this is d2 Jn of ax dAx squared plus 1 over ax dJn of ax dAx plus 1 minus n squared over a squared x squared Jn of ax equals 0. And so now we have a factor of a squared everywhere in the denominator except here. I don't know how I can show this board and that board because this one will block it. Maybe I'll just go up a little bit. So if we have this equation, we can rewrite that as x d2Jn of ax dx squared. So we're multiplying the whole equation by x a squared. And that gives us so 1 just becomes a squared x, and this becomes minus n squared over x Jn of ax equals 0. So that's Bessel's equation with a parameter a scaling the independent variable. And if we write this in self-adjoint form, we can write this as d by dx of x Jn of ax that is to say d by dx of x, well, in the full self-adjoint form, it's minus d by dx of x dJn of ax dx plus n squared over x Jn of ax equals a squared x Jn of ax. So that's Bessel's equation with a parameter in self-adjoint form. Is there some problem you'd like me to do, particularly of the problems at the end of chapter? At the end of this chapter? let's see, why don't I try this board down here? Let's, suppose you set y equal to jn of ax. Then the equation I just derived actually is x y prime prime plus a squared x minus n squared over x, y is 0. We multiply this equation by x y prime. So now we have x y prime times x y prime prime plus x y prime times a squared x minus n squared over x y. And now we're going to integrate this from 0 to b. So we have integral 0 to b of all of this dx equals 0. And then what we're going to do is we're going to set AB equal to the mth 0 of the nth Bessel function. So that, that is to say, Jn of AB is Jn of Znm, and that's equal to 0. So what do we get here? So this is xy prime, and then we have that dx. So this integral here in the first part is the integral of xy prime dxy prime. And the rest of the integral is integral 0 to b of, well, of course I've got the solution in front of me here, so instead of trying to invent it, I probably should just follow my notes. But in any event, one sees that this first part is just simply going to be xy prime at b minus xy prime at x equals b, x equals 0. Well, this one is 0, and this is jn prime at znm. But dealing with this is a little more complicated. And so what we do is we take that Bessel function over there, the Bessel's equation over there, multiply it by x jn prime of ax, and so this equation in terms of the jn's is minus x jn prime of ax times x jn prime of ax prime plus n squared jn prime of ax jn of ax, and then we have that equal to a squared x squared jn prime of ax jn of ax. So then if we integrate, we get this part I already did, and so what we get is minus a half x jn prime of x, actually, now that I think about it, I did the integral incorrectly. It's, when you do this integral, what you get is this squared over 2. And so what we have here is this quantity squared evaluated at b and 0. Then we also get n squared over 2, jn squared of ax evaluated at 0 and b. And then this is equal to this integral, which is then a squared integral 0 to b of x squared jn prime of ax jn of ax dx. So this part we don't do, but we do this one. You see, this is jn djn effectively, and consequently we get jn squared over 2. And so now, if we recall that AB is JNM, and for x equals 0, the Bessel functions are either 0 when n is greater than 0, or when n equals 0, or they're 1, it's 1, but then you have a 0 here. So this term is 0, and the term there, though, is not 0, and so what we have is then, let's see, I've got so what we have is minus a half x, x djn of ax dx squared evaluated at x equals ax equals znm. That's that term. This vanishes, equals this. So we have then a squared integral 0 to b x squared j n prime of ax j n of ax dx. But that is a squared integral 0 to b of x squared 1/2 j n squared of ax derivative dx. And so over here, what we have is minus a half z n m squared jn prime of znm and that's then equal to we get that that's equal to minus a squared integral 0 to b x jn squared of ax dx. Anyway, the final result is that the integral 0 to b of x jn squared of ax dx is znm squared over 2a squared little too involved. Is there some particular problem you'd like me to do?
Not off the top of my head, no. I can't think of one.
Well, let me get another piece of chalk. So we might look at 14 if you want me to do it. So 14 says lambda equal to z squared over r sub d squared. I'm going to set rho equal to z r over r sub d. And we're going to set u of r equal to jn of rho. And the equation that occurs in one of the problems is minus r u prime prime plus n squared u over r is lambda ru. And we want to see that this turns into Bessel's equation 10.29. And so we'll start with this equation. Which is d by d minus d by dr of rho du d rho. So now rho and r are linearly related, and so we can change r d by dr into rho d by d rho. And then this is then still n squared u over r equals lambda ru. And using the relation between rho and r, this is minus z over rd, changing r to d by dr to d by d rho. This becomes d by d rho, rho du d rho plus z over rd n squared u over rho equals lambda rd over z u. So now we've got everything written in terms of rho and u. And we're going to set u equal to j, u of r equal to jn of rho. So this was actually u of r. And so that means that what we have is minus z over rd dd rho of rho djn of rho d rho plus z over rd n squared jn of rho over rho is lambda rd over z jn of rho. And we've got a common factor of z over rd, and we get rid of that, we have minus d by d rho of rho djn of rho d rho plus n squared is n squared over rho minus, well, no, let me say that. This is then n squared Jn of rho over rho is lambda Rd squared over z squared Jn of rho. And so this is basically in self-adjoint form because of this structure here. The function p is just the identity function. P of rho is just rho. And so this so I think we're done with that. So 15 was a homework problem, but I don't know, do you want to see 16? Problem 16. Or equivalently 17, 16, 17, 19, 20. Which Which?
19.
19? Okay, so we've got a TE field. So TVE field means that the direction, that the electric field in the direction of motion vanishes. And so that means that EZ is 0. I switched notation in this chapter, and I was writing, originally I had things like this, EZ comma rho for the rho derivative of the Z component of EZ. And then I thought, well, let's turn that into EZ sub rho, using the subscript notation for derivatives, because that's clearer. But when I did that, I left some of these Z's as subscripts, and so in particular here, what we actually have is EZ equals 0, and the Z component of B is then Jn of square root of omega squared over C squared minus K squared times rho E to the IN V E to the I Kz minus omega T. So this is propagation down the z-axis. This is the regular E to the I and V around the azimuthal angle. And we want to show that this satisfies the right boundary conditions, 1058, if square root of omega squared over C squared minus K squared, R being the diameter of the radius or the type of the cylindrical waveguide. And so we're saying that this is a 0, M0 of the nth, of the derivative of the nth Bessel function. So in other words, the Jn prime of Z prime Nm equals 0. So this means the derivative, this means the prime on Z here just means it's a 0 of the derivative of the Bessel function, not the 0 of the Bessel function. So what do we do? First of all, since EZ equals 0, the boundary condition EZ at R phi equals 0 is obvious because EZ vanishes, because it's transverse to electric. So now we go to the formulas 1060, which show that what E phi, and again, I should have used superscripts, E phi of R and phi, and E rho of R and phi, that these are proportional to the rho derivative of the z component of this, which is square root of omega squared over c squared minus k squared times j n prime of square root of omega squared over c squared minus k squared r the I n p e to the I kz minus omega t. And because this thing is going to vanish if this is a 0 of the Bessel, of the derivative of the Bessel function. So we're basically done, and what you have to do is look in the text and see that E phi and B rho are proportional to the rho derivative of BZ. And I have the text over there. So if we look at those equations, for 1060, so there's 1060, and that shows you that E phi is proportional to EZ, which is 0, and then the rho derivative of EZ. And it also shows that B rho, which is this one, is proportional to EZ, which vanishes for TE modes, and then the rest of it is the rho derivative of BZ. And if you then take the rho derivative of BZ, the rho derivative of BZ is just what I wrote down there. So that's basically the solution for problem 19. Now, what about another problem? Or do you want me to discuss something else? Group theory, GR, and integrals, probability and statistics, or should we just do more Bessel function examples? All right, if we want to do more Bessel function examples, why don't you pick one? Number 20 is a long story. If you want, I'll do it. And I have to warn you that it's a long story. let me just pick one. Suppose we look at 27 just briefly. 27 is a short one. What we want to do is we want to show that minus 1 to the L, dl of sine rho, rho to the L is sine of rho minus pi L over 2. And show that this, and complete the derivation of a certain approximation for the spherical Bessel function. So basically this quantity here is minus 1 to the L dl d rho to the L of e to the I rho minus e to the minus I rho over 2I. Let me put the 2I out there. By the way, this is one trick that you should keep in mind, namely that if you're asked to do something complicated with a sine or a cosine or a cosh or a sinh, it's usually a good idea to go quickly to the representation of the sine in terms of things that are easy to differentiate and integrate, rather than to say with something that changes from sine to cosine and has unpredictable minus signs coming in. Well, they are predictable, but it's not a trivial matter. So this expression here then is 1 over 2I. Well, if we differentiate this, d rho to we differentiate L times, we bring down I to the L. And so this is, and then we have a minus 1 to the L. So what we have here is minus I to the L, e to the I rho for the first term. And the second term is, there we're bringing down minus I to the L, and that means what we have here is I to the L, e to the minus I rho, and all of this is divided by 2I, sorry. And now we can rewrite this as 1 over 2I. Minus I is e to the minus I pi over 2, and we're raising that to the power L. And we have e to the I rho, and then we have minus, and this is e to the I pi over 2, and the whole thing raised to the power L, e to the minus I rho. And so now we see that this is 1 over 2I e to the I rho minus L pi over 2. And the other term here is minus e to the minus I rho minus L pi over 2, because this one has a plus sign. Now we see that this is just sine of rho minus pi L over 2. And so that occurred within a certain, that problem was within a certain context, and the context was equation 1075, which had to do with spherical Bessel functions. Well, sometimes I add or subtract an equation, and so this is 1074 here. So the idea is that if this is here's an expression for the spherical Bessel function. In fact, it's Rayleigh's expression for the spherical Bessel function. And if you differentiate the 1 over x, you're going to get successive powers of x in the denominator, and so at large x, it's going to vanish. So what you do if you want to approximate JL for large x, you let all the derivatives act on sine, and so that means you have L derivatives acting on sine of x, and so that gives you where is the expression? I don't find the equation that we're trying to. Ah, there it is. It's 1078 instead of 1076. Anyway, so we see then that the spherical Bessel function at large rho, you let the d by d rho act on sine of rho exclusively, and that gives you the sine of rho minus pi L over 2. And then what's left over? What's left over is a 1 over rho, and then rho to the L divided by rho to the L, so that's just 1 over rho. And then we absorb the minus 1 to the L into the final answer. So the minus 1 to the L that starts out here just disappears into that. So that's how that works. I think it might be more instructive if I go back to the problem that I said was quite long, but I think might be more instructive. So let's look at problem 20. And what is problem 20? Problem 20 says that L is an integer, and square root of omega squared over c squared minus pi squared L squared over h squared times r is one of the zeros. Well, it's the nth zero of the derivative of the nth Bessel function. And what we're going to say here is we want to show that EZ and BZ, that EZ is 0 and that BZ is Jn of Z prime and M rho over R e to the I phi sine L pi Z over H e to the minus I omega T. We want to show that these satisfy both boundary conditions at rho equals R and the other ones at Z equal to 0. At Z equals 0 and Z equal to H. So what we're considering here is a cylinder of height H and radius R. So this is a cylindrical cavity. And we want to say that these satisfy, essentially that B satisfies the wave equation. And so what we're going to use is Maxwell's equations in vacuum. So these are Maxwell's equations in vacuum. And once again, we have a TE field, so the Z component of E is 0, and so the boundary conditions, so E automatically satisfies the boundary conditions. So the only thing we need to worry about is B sub rho. So in other words, we've got B sub rho then is the perpendicular component of the component of the magnetic field that's perpendicular to the conducting surface, and we need to refer to those boundary conditions. I went too far. My memory is that B sub rho should vanish. Let's just make sure. Right, B sub rho, the rho component of B should vanish at the conducting surface. The perpendicular component of the magnetic field, perpendicular to a perfect conductor, is supposed to vanish. So we want B to vanish. But I don't know, B automatically vanishes because when rho is equal to R, that's right, we just had J. Well, that's, you see, that's JZ. We have to figure out what B rho is. We need to figure out what B rho is when rho is equal to R. So we want to check that B rho of R phi is equal to 0. This is what we want to get. And what we're given is BZ, and so we can compute the rho derivative of BZ. And if we compute that rho derivative, then since BZ is given by this just tosses out the factor of G prime NM over rho over R, and the rest of it remains the same. So this is, and it's J prime N, and this at R and phi, setting rho equal to R, we just get C prime and M sine L pi Z H minus I omega T. So that's obviously 0 because Z prime is 0 of J prime. Now the sign of pi Z in the solution for BZ, this means that we have that BZ is equal to 0 when Z is equal to 0, and also when Z is equal to H, because then we have sine of 0 or sine of L pi. And sine vanishes at 0 and it multiples pi. So we've satisfied that condition because you see the magnetic field has to vanish when it's perpendicular to the conducting surface. That is both at rho equal to R and at Z equal to H and Z equal to 0. And we verified that. But what we now have to do is check what the electric conditions are. And the electric conditions are that the electric field parallel to the surface of the conductor should vanish. And so that means, well, that means that EZ should vanish when rho is equal to R, but EZ is automatically 0 because this is a TE field. So we have to verify that E rho is equal to 0 when Z is equal to 0 or H. And so that means we need to figure out what is E rho at Z equal to 0, because it's supposed to be 0, and E rho at Z equal to H is also supposed to be equal to 0. So we have to prove that. Now, we had formulas, I have them listed as 1060 here. Right. These formulas express E rho in terms of the rho derivative of Z and in terms of BZ. Well, the rho derivative of Z is 0 because EZ is 0. And so this is just this is just BZ, and I somehow have the rho derivative of E. In my solution, I have that as the phi derivative of B, and that's not what we're seeing here. So, I don't know, there's something wrong here. There's a typo in either the solution or in the book there. So let's try the next one. Right, the next one is right. So, E phi, the phi component of E, and that also has to vanish. That has to vanish when rho is equal to R, because the phi component of E is the component of E that's parallel to the surface of the conductor. And the phi component of E is the rho derivative of BZ, apart from the factor. So let's look at that. What we have then is that E phi is I omega, the rho derivative of BZ divided by K squared minus omega squared over C squared. And now here's BZ. If we take the rho derivative of that, well, the rho derivative of this is obvious. It's just it's just BZ times Z prime over R. And that obviously vanishes when Z is equal to 0 and Z equal to H. And it also vanishes when rho is equal to R. We want, because when rho is equal to R, when we take the rho derivative, it turns Jn into Jn prime. We set rho equal to R, this is just that evaluated here, so that's 0. And so that means that E phi vanishes when rho is equal to R. So we want to check, though, perhaps that BZ satisfies the wave equation. And so what is the wave equation when it hits this? In other words, what we want to show is that minus Laplacian on BZ is equal to minus the double derivative of Z with respect to time, divided by C squared, and that's just omega squared over C squared, times the Z component of B. And So the question is, what is the Laplacian? So this part is obvious. What's the Laplacian of BZ? And the Laplacian of BZ then, with a minus sign, is minus 1 over rho d by d rho of rho BZ, partial BZ, partial rho, plus 1 over rho squared, partial 2BZ, partial B squared, plus partial 2BZ, partial Z squared. And the derivative with respect to phi is just pulls down an I. Actually, I must have written this incorrectly because there's an N here. This is I N phi. So this pulls down a minus N squared BZ. And the Z component, well, that pulls out in L pi over H squared together with a minus sign. So that's minus L squared pi squared over H squared BZ. And this term we can't do anything about. But the fact that this plus this is equal to that, that's basically Bessel's equation. And it's Bessel's equation for Jn of A rho, where A is equal to square root of omega squared over C squared minus L squared pi squared over H squared, not H bar squared. And that's satisfied because this quantity we set equal to Z prime NM over R. And so what we've got finally is a formula for the resonant frequencies, mainly that omega N M L, N being the azimuthal quantum number, L being the vertical quantum number, and N, I guess, the radial quantum number. This is equal to C times the square root of Z prime N M squared over R squared plus pi squared L squared over H squared. So those are the resonant frequencies of the cavity. So you can see these are techniques that if you're interested in electronics or, for that matter, optics. These are important concepts and reasons. So let's see, we have a few minutes left, enough to explain the concept, perhaps, if somebody has a conceptual question. minutes left. What? Oh, was that signed? I might go back to this definition. The Bessel functions of the second kind are given by this formula here. And when nu approaches n, we have 0 over 0. And so you have to differentiate the numerator and the denominator and take the ratio. And when you do that, you get this derivative plus this derivative with a factor there. These all diverge at small z equals 0. Whereas the Bessel functions are either 0 or 1 at z equals 0. So these satisfy Bessel's equation, but don't satisfy the boundary conditions of Bessel's self-adjoint system. Okay, so I guess that's it. No further questions? I don't know why I use the adverb further or adjective further. All right, let's turn it off.